Hi guys, this video is on the difference between worst case analysis and amortized analysis. This comes into play in analyzing the vector data structure that we just defined, so we want to define this concept before we try to analyze the vector. Remember that we've already talked about worst case time. Worst case time means the maximum amount of time an operation could take. In other words, the slowest it could ever be. And that's usually a fair measure. I argued in that video that this is a good way to go. However, sometimes worst case analysis can be unfair. It can give us an unrealistic picture of how slow an operation is. This happens in a specific situation when we have repeated operations done over and over again. Almost all of them are fast, but rare operations are slow. And what happens there is if we focus on the worst case, we would focus entirely on these rare slow operations. And while it would be true that that would be the worst case time of one operation, it paints a pessimistic picture that all of the operations are that slow. And the story is different. Really, the average is much better because most are fast and there's just these rare slow operations that are making the worst case look bad. Let me make an analogy to real life. Let's view the process of buying soda for yourself as one of these repeated operations. So the operation I'm going to repeat is if I'm out of soda, I'm going to go to the supermarket and buy a 12-pack. I'm going to say that costs $4. Then, now that I know I have soda cans in my house, I drink one soda. So let's say I start from nothing, I don't have any soda yet, and I do this. The first time I try to drink a can of soda, I have to go to the store and buy, so it costs $4. Then, the next time I drink soda, I have 11 cans left over, so I can drink one for free. So the first operation costs $4, then I get a free. And there will be a total of 11 free drinks before I have to go to the store again and spend $4. The pattern is you spend $4 once, and then you get to spend $0 11 times, and that repeats indefinitely. The worst case cost of this is $4, right? The most out of pocket I ever am is $4 when one of these events occurs. However, it's not really fair to say that every time I drink a can of soda, it's costing me $4 because that's ignoring the fact that you have 11 free drinks. So a better measure would be what accountants call the amortized cost, and that's basically the unit price. How much am I paying per soda can? The unit price is the package price, $4 for the 12 pack, divided by the number of units in the package, which is 12. So the unit price, the dollar per can of soda would be $4 divided by 12, which comes out to about 33 cents per drink. And I would say that's a more fair measure of how much I'm spending on soda, about 33 cents every time I drink a soda, even though occasionally I have to come up with $4. Amortized time efficiency uses this kind of idea and applies it to these big O asymptotic analyses. The amortized cost of one operation is the average cost of a sufficiently long sequence of these repeated operations. So, in the previous example, in a sequence of 12 drinks, the amortized cost is 33 cents. If you go through the whole cycle of drinking 12 sodas, on average, you're spending 33 cents. Amortized time is the average big O time of a sufficiently long sequence of operations, enough operations to go through the whole cycle of whatever we're dealing with. In general, if big O of C operations take a total of big O t time, then the amortized time of one of them is big O of t divided by C. It's the same unit price calculation as before. I'm saying C for cost, T for time, or C for count, the number of operations, T is for time. Often, both of those big O expressions are big O of n. So if I have big O of n operations and they take a total of big O of n time, then the amortized time of one of them is that division, big O of n divided by big O of n, which comes out to big O of 1 amortized time. Here's what this kind of a pattern would look like if we were to plot the time of each individual operation. So what I've got going here is a count of how many operations I've performed, and on the vertical axis, the amount of time it takes to perform one operation. I've got a cycle here. This is synthesized to make the point. Let's say I have a kind of a situation where you get 4 fast operations and then the fifth one is slow, and then you get 4 fast operations and then the fifth one is slow. The blue line here shows what the observed time of these operations would look like. You'd have kind of a heartbeat pattern where it's super fast for a while and then slow, and then super fast for a while and then slow. But if you average that out, it averages out to a constant amount. Which is better between the two? Well, all things being equal, big O of 1 worst case time is better than big O of 1 amortized time. If we had our choice, all data structure operations would be big O of 1 worst case time, and we would never have these kind of alternating fast, slow kind of situations that lead to amortized time bounds. However, there are worthwhile data structures that have these on again, off again, fast, slow patterns, and therefore their time efficiency has these amortized time bounds. And notably is the vector, and the vector is probably the most practical data structure. In languages like C++ and Java, we use the vector as our general purpose data structure to store most things. So if we completely ruled out and banned any data structure that has an amortized time bound, we wouldn't be able to use the vector, and that doesn't seem like a good choice. And that's because in many practical applications, this amortized time behavior is perfectly acceptable. It doesn't really make a difference. For example, when you compile a program, that's a relatively slow computation. And when you say compile my C++ program, the compiler does a whole lot of stuff, so it probably does many vector operations. It's probably building a lot of vectors and destroying them, so it might do a million individual vector operations. You don't really care if one particular vector operation is slower than the rest. You only care about how long the whole process takes. You just care about the total amount of time. So in a situation like that, it doesn't really matter that some vector adds are slower than others. You just care that the whole process is fast, and the vector can achieve that. Altogether, it's pretty fast, even though there's variation in how fast each individual operation is.